Hello, my name is Alexis. My fun proof for today is going to be based on my fractal geometry homework that I did this week. And that is to prove that the sets n and z are equivalent and thus showing that z is countable. So to start off the proof, we have to assume both n and z are non-empty sets. Also assume that n is countable and its set starts at 1, since we know that z is both negative and positive integers and 0. In order to show that they're equivalent, they need to have that bijection, which means that they are 1 to 1 and onto. So suppose first we assign n equals 1 to f of n equals 0, which is our z. And since 0 is a special case that is neither odd or even, so our mapping is going to look like when n equals 1, it goes to z equals 0. Now suppose we assign all even n values to z positive and all odd n values to z negative. We can construct two different functions to demonstrate how they'll map, which are listed here. So we have f of n is equal to n minus n divided by 2 when n is even, and for f of n equal to negative, in parentheses, n minus 1 minus n minus 1 divided by 2 when n is odd. Using the functions that I just stated, our mapping will appear as follows. So we already have our 1, when n equals 1, it goes to 0. But for n equals 2, it goes to 1. When n equals 3, it goes to negative 1, and it'll continue that way to infinity, as you can see here. Now let's show these functions are 1 to 1. So using our first f of n, when n is even, let's show that f of x equals f of y. So when we plug it into our equation, we have our original function, and it's going to be x minus x divided by 2, which is equal to y minus y divided by 2. When we can factor out x and y on both sides, so when we simplify the numbers, we get 1/2, and then when we multiply 2 on both sides, we get x equals y. So therefore, f of n for even numbers is 1 to 1. Now we need to show that f of n for odd numbers is 1 to 1. So again, we have our f of x is equal to f of y, and when we plug in our equation, we can do a similar thing where we factor out the x minus 1, and we can simplify the numerical stuff to 1/2 and pull that outside, so we get a negative 1/2 on both sides. And then when we multiply negative 2 to both sides, we get x minus 1 equals y minus 1. And when we add a 1 to both sides, we get x equals y. So therefore, both f of n functions are 1 to 1. And so now that we have proved that, we need to show that our functions are onto. And to prove this, we need to show that there is an x in n such that f of x equals y for any x and y. Any y in z. First, let's test the functions for our even numbers. So we have f of x equals y. And when we plug in our even equation, we have x minus x divided by 2 is equal to y. We can factor out our x, simplify the numerics again, multiply 2 on both sides, and we're left with x equals 2y, which we can plug into our original function. So we'll have the same function again, x minus x divided by 2 equals y, but this time we can plug in our x value into the equation. So we get 2y minus 2y divided by 2. We can simplify this division, so we're left with y, and 2y minus y is y, so y equals y. Therefore, f of n for even numbers is onto, and we can do a similar thing again for odd numbers. So again, we can factor out our x minus 1. We are left with a negative 1/2 on the outside. We can multiply by negative 2. Simplify again, and our x is equal to negative 2y plus 1. And we can again plug this into our original function. So we will end up with this extremely long function right here, which is a negative on the outside, and then negative 2y plus 1 minus 1 minus negative 2y plus 1 minus 1 divided by 2. And when we simplify, we get a similar structure as the previous one, and we divide this 2 right here. And at the end, we're left with a negative 2y plus y. We can then distribute the negative into our equation just to get rid of it. And then we have 2y minus y equal to y, and we have y equal to y at the end. So therefore, both of our functions are onto. And since both of them are since both functions are one-to-one and onto, this demonstrates that our n to z is a bijection. Therefore, they're equivalent according to the definition that states that two non-empty sets are equivalent if there is a bijection from n to z. And since we previously stated at the beginning that n is countable and both sets are equivalent, this infers that z is countable. Therefore, z is countable. And that is the end of my proof. Thank you.